Welcome to our video on vector addition. Now let's discuss how we add one vector to another. To help you understand this topic, I'll start by using one of the simpler vector quantities, displacement. So jump ahead in your notes, go to page 9 where you see example 5. So imagine you're driving down a very grid-like city and your car moves 4 kilometers east, then after that 3 kilometers south, then 2 kilometers west, and then finally the last leg is 1 kilometer north. And you're asked to find what is the displacement of the car. Now, displacement is the change in position. That's from the initial starting point to the very final place it is. Now remember that displacement is not the same as distance, and we'll get into this a lot more into the next chapter, but imagine if you were to, say, walk 3 kilometers north from your front door, it doesn't get you to the same place if you were to go 3 kilometers southeast. So the distance that you walked is 3 kilometers, but your displacement would not be the same because it's not in the same place. All right, now to find the displacement of the car after all of these different legs, we're going to need to add each of these individual vectors or displacements. So let's start by drawing the first vector, which is 4 kilometers east. Now we're given over here an XY coordinate system. And often you'll have to draw your own coordinate system when you solve problems like this. Let's choose over here where it says X to the right, that positive x-axis, let's choose that to be east. And then the positive y-axis, let's represent that with a north. So therefore south would be on the negative y-axis and west would be on the negative x-axis. Now, another assumption we can make is you can decide wherever you want to start the car. And an ideal position would be at the origin. So let's assume that when the car starts its journey, it's going to leave the origin and it's going to move 4 kilometers east. So how do we represent this 4 kilometers east? Remember, it has a magnitude and a direction. It's a vector. And vectors are represented with what? Arrows. So get your ruler out and in your notes and draw a 4 kilometer vector going in the easterly direction. That's going to the right. So I'm going to shade in here, right along here. This is an arrow going to the right, and that's our first vector. I'll just label that as vector A. That's the first one, which is 4 kilometers east. Now after that, the car then moves 3 kilometers south. Now we draw the second arrow starting where the first one ended. In other words, you're going to put the tail of your second arrow at the tip of the first. So we're now moving 3 kilometers south. That's going down the negative y-axis. And so we're now going to draw an arrow going 3 units down. That's vector B. So you see that I put the tail of my second vector at the tip of my first vector. And after that displacement, the car moves 2 kilometers west. So now we're going to draw an arrow 2 kilometers to the west, which is to the left. Again, leaving the tip of that last vector we were using. And then finally, the car moves 1 kilometer north. So we're going to draw the final vector going up here, and there's vector D right there. So what is the displacement of the car? Well, the displacement is that single vector that would go from the very starting point, the initial position, to the very final spot that it ends, the final position. So this would represent your final vector. This is your resultant, as we call it. And we'll just label that with a capital R for resultant. The resultant is also known as the vector sum. So let's go back to the part of the notes where we started earlier in the video and define some of the things we just did. So moving back here to where we had, whoops, I'm just trying to move up here, to where it says vector addition, we see what is the resultant. And the resultant is the sum of 2 or more vectors. And we can represent this symbolically. you can write it, for example, as vector r, which is our resultant, as the sum of vector A plus vector B plus vector C plus vector D. And you'll notice that I'm putting vector symbols all above these letters because these are vectors. We're not adding numbers like scalars, we're adding vectors where you have to take in consideration both the magnitude and direction. For example, if you jump back again to the problem we were looking at earlier, the sum of vector A plus B plus C plus D gave you this one single vector here. Now, if you were to simply just add up the numbers of 4 plus 3 plus 2 plus 1, that would not be the length of the resultant. And that would be giving you with what is known as the distance that you actually traveled. But the displacement is this single vector that has a length, a magnitude, and a direction. So what was the method that we utilized to find this resultant vector? Well, we typically call it the tip-to-tail method. So once again, jump back to your notes earlier a few pages. When we add vectors graphically, like on that grid, we use what is known as the tip-to-tail method. So what we're doing in this case is we're always arranging the vectors so they're tip to tail, so that the tip of one points to the tail of the next. That's probably better shown. So let's practice now doing example 1 and then example 2 by using the tip to tail method. So I'm going to start by doing example 1 here. And I'm going to show the vector addition of vector A plus vector B. Now they're both arranged leaving the same place. So you need to arrange these vectors so that the tail of your second vector is at the tip of the first vector. Now you can, if you wish, remove B, I guess, or retransplant it so that its tail is over there. Now when you retransplant or move this vector, you need to make sure that you keep two things the same length of that arrow and the same direction of that arrow. Just so it's a little bit easier for you to visualize, I'll just redraw A over here with about the same magnitude as this. And now I'm going to take vector B and move it so that it is at the tail, its tail is at the tip of vector A. And again, keeping the same length approximately. So there's vector B. So the resultant vector will be pointing from the tail of the very first vector to the tip of the final one. So this is your resultant vector, which I'll represent with a vector r, which is equal to vector A plus vector B. But what would happen if I were to reverse the addition order and say I added B, then A to that? There's vector B, and now I'll add vector A to the tip of B. And there I'll put vector A, and now let's show the resultant vector R. Once again, it will start at the very tail of the first vector to the very tip of the last vector I added. And if you look at this vector R here and this vector R here, they should be the same size and the same orientation or direction. So really, this vector r, which is vector b plus vector a, is exactly the same as adding them in the reverse order. Won't make any difference really. Okay, what happens when we add several vectors like we have a, b, c, d? Go ahead and do that. So first what I'll do is I'll start with vector c drawn out, and then then add vector b to that. There's vector b, and now I'll add vector d to it, and there we go. And lastly, we'll add vector a. And there we go. We have vector c plus b plus d plus a, and the resultant would be from the tail of the first vector to the very tip of the final vector that you used. So this resultant would be right here. And the resultant would be the sum of vector c plus b plus d plus a in that order. But what would happen if you were to change the order and add, say, vector d, then c, then b, and then a? Would you get the same answer? Try it out. There's vector d plus vector c plus vector b, and finally vector a. And so the resultant would be from the tail of the first vector to the tip of the final vector we used. And if you compare this resultant vector to the other resultant vector in a different addition order, you'll find they're the same. So hopefully you believe me that if you reverse the order, it doesn't make any difference. Vectors can be added in any order. Do you remember what we call that in mathematics? Go to the next page in your notes. And you can see at the top of your page where it says, does the order of addition matter? And the answer is hopefully a resounding no. You can add them in any order. So vectors, or vector math, will obey the associative and the commutative laws of addition. Let's go a bit further now with our vector math and discuss how we subtract vectors. It is commonly asked in AP Physics to find the difference between two vectors. For example, we might have two positions in a x-coordinate plane with position, say, A here, and I don't know, position here, B, and a initial displacement here, x sub I, and a final displacement, x sub final. And we might be asked to find the displacement, which is the difference between the final position and the initial position. But before we get into all this vector subtraction with displacements, I should point out some other key ideas. So let me just erase my diagram. And let's discuss what would happen if we were to, say, multiply a vector by a scalar quantity, which is basically a number. Let's say I have vector A. I'll make it about 2 units to the right. But now I decide to multiply it by 2. So what would vector 2A look like? Take a guess. Draw it. Hopefully you guessed it. It's twice as long as the original vector A. So when you multiply a vector by a scalar quantity, number, basically 2 in this case, the length of the vector changes by the factor that you multiplied it by. But what would happen now if you take it one step further and we were to multiply the vector A by a negative number, like, say, negative 3A? What does that look like? Take an educated guess. Put it down. So hopefully you drew a vector that was 3 times as long as the original vector, and then maybe you noticed the idea of what happens when you put a negative. When you put a negative in front of that vector, then it reverses the direction of your original vector. So when you multiply a vector by a negative number, the effect is that it reverses the direction of the original vector. Why do you think this might be important when we subtract vectors? Let's say I were to subtract two vectors, like vector B minus vector A, and I want to know how to solve that. So to show this, let's do an example. Draw two vectors. I'll draw vector A about 3 units going diagonally upwards on my page, and vector B about 2 units going diagonally downwards on my page. So if we were to subtract vector B from vector A, how would we do it? Well, it's the same thing that you were doing before, but with a little bit of a twist. You take vector B, and then you add the negative of vector A to it, and that's the same as doing B minus vector A. The negative vector A has the same magnitude or length as vector A, but it's in the opposite direction as vector A. So let's redraw vector B over here, and at the tip of vector B, we're going to add negative vector A to it. Notice that this vector negative A has the same length as A, but is 180 degrees in the other direction. And we know it's in the opposite direction by showing this negative in here. So the resultant of B minus A vectors would look like a vector that comes from the tail of the first vector B to the very tip of our last vector, negative a. So when you need to find the difference between two vectors, when you need to subtract two vectors, you need to add the negative of the next vector that you're trying to have as your second vector, which you're subtracting. Okay, our last topic in this already rather long video. We're going to discuss a method of adding two vectors that are concurrent. If you have two vectors, let's say here is vector A, and then over here is vector B, but they already happen to have their tails joined up together. They're leaving the same place, and hence they're called concurrent vectors. Now, you'll see this type of problem very often with forces. You might have vector A represent one string pulling an object, and then vector B be another string pulling on that same object, and then we're asked to find what is the resultant force of these two vector forces. What would be that one single force that would be the combination of these two individual forces? Now, to solve this problem by tip-to-tail method, you might take, say, vector A and retransplant it over here. Or you could take vector B and retransplant it over here. In essence, what you would be doing is that you could be just drawing a parallel line right along here and another parallel line over here. This line would be parallel to vector A, and this line here would be parallel to vector B, and you would have constructed a parallelogram. The resultant vector would be an arrow that starts at the tails of the two vectors, moving along the diagonal of the parallelogram to the other corner. The length of that diagonal would represent the magnitude of the vector, and don't forget you'd have to put a direction on that vector because it has a direction as well. I find this parallelogram method very convenient when you have two concurrent vectors. However, if you have to add three or more vectors, like vector A plus B plus C plus D, then it's not so convenient because you would have to first find the resultant of A and B using the parallelogram method, which would be the sum of vectors A and B, then add this vector to, say, vector C, ending up with a vector sum of A plus B plus C now, and then your final resultant of vector A plus B plus C plus D. And I imagine you could find that to be quite messy if you were to do all of that work in the same place. And in the next video, you're going to learn about the component method that does it beautifully, mathematically. And that's it for our discussion of vector math graphically.